Thank you all for braving the snow. They don't call it silicone slopes, I guess, for nothing here in Salt Lake City. I love the co-located events with Kubecon, don't you? It's an amazing time to really embrace and smear the open source technologies on you and dive in and get lost and come back for more. It's really a good time, and please take advantage of it this week. We're going to end up talking. I'm Mike Barrett. I run the business that looks after OpenShift. I'm shared the stage with Derek Carr.
Yeah, and I'm the lead architect for OpenShift.
And later we'll have Ronald come up and he'll run some demonstrations for us. But we're going to talk about platform shifts. And the beautiful thing about platforms is that when you work on a platform, from time to time you may think, wow, this platform is getting massive. It is growing. I don't necessarily know if we should go there, but the best part about it, and I've worked on them my entire adult life, is as time passes and time washes over you in these like 5-year spans, you look back and you're like, wow, that was obvious. That was completely obvious that it was gonna go in that direction. And we're gonna talk about some things that are affecting the platform in 2025. And these are the things that we get to really grapple with as we figure out what to invest in and what not to invest in and where to go. So the first one is artificial intelligence, right? And OpenShift has been on a journey with a lot of its open source projects. It started to get involved in AI, I think, with the Open Data Hub, bringing in Kubeflow and some of those technologies, bringing in Jupyter, bringing in a lot of the things that helped you in 2018, 2019, 2020, invest in predictive AI. A lot of the lightweight MLs were on the platform taking advantage of some hardware acceleration. And then something magic happened in 2022 and 2023 where large language models just really took off. And we have a lot of users coming to the platform saying, look, I need a new way to interact with these large language models. What have you seen that's really driving some change at the platform level?
Yeah, thanks, Mike. So before I give that direct answer, I guess Mike and I have been at KubeCons for a very, very long time. I think we were both probably at the first KubeCon. Definitely, I remember being in Seattle back in, I guess it was 2015. And the scope of problems, Mike and I were chatting before we got on the stage here, that we were discussing in Kubernetes was far smaller than it presently is. Like the size of clusters were smaller. The types of workloads that were coming on the cluster were kind of, I want to say more traditional or simplistic in the sense that it was a lot of just request-serving web applications. And then there was a big push from Red Hat and others in the industry to try to bring storage onto Kubernetes. And a lot of people thought that was nuts. How can you run storage solutions on the platform? And then you start to see these core APIs in Kubernetes evolve. Like in the first set of APIs in Kube 1.0, and I see some other maintainers in the audience, I think there was like 3, right? You had maybe deployments, maybe replica sets, maybe a pod. And then slowly, and a few years later, you get persistent volumes, persistent volume claims. Then we start to kind of touch our feet a little bit to the fire around batch processing. You get little primitive APIs around jobs. But then the huge community explodes around us to support things like Tecton and pipelines that build on these lower level primitives. So the platform slowly evolves as the industry kind of asks it to do more and more. Then I think a number of us, including co-presenter Mrunal here, got deeply involved in trying to get performance sensitive applications available on the platform. And that was largely out of things like the telco industries, right? That push you really hard to make sure my CPU, my network, and my hardware needs to be deeply aligned. And each time you do one of these new steps, I remember being in conversation with Mike like, oh man, this is super hard. I don't want to do all this. Do we have to do this workload? Do we have to make this happen? But each step that we take supports the next step afterwards. So the nice thing about the AI moment that's happening right now is it's building on all of those primitives we built in the past. So the fact that we can support batch processing now means, oh, it's a viable platform for training. The fact that we can support devices and CPU alignment, all these things, you're like, oh, I'm going to use this platform for inferencing. And so the big effort that we're really excited right now in the community that we're tracking is around this concept called dynamic resource allocation.
So remember that name. That's going to be huge.
You might hear it by the term DRA, and a lot of people in the maintainer community will joke that it's not even KubeCon, it's just like DRA-con at this point. So Kubernetes traditionally has had a relatively simplistic device model. It was called device plugins. A number of us in past KubeCons were working on that. And you could advertise the device in a rather simplistic, opaque way. You could say, I would like a GPU, and give me 2 of them, right? But the big thing that's happened now with the AI revolution here is, like, one, the amount of GPUs that are coming into the data center are massive, and people are really looking to apply them way more often. And these devices are expensive, and so you want to get the most out of them. So what the dynamic resource allocation does in Kubernetes, it allows you to kind of have, in the same way that CSI gave you this idea of I would like a volume, and the provider gives you the volume, dynamic resource allocation allows you to say, I would like a resource of a particular type. I might want a GPU with this many cores, this much memory in this particular family. And then it's the platform's job to make it happen for you. So it gives you way more fine-grained scheduling and way more fine-grained ability to slice and dice the emergent hardware coming into your data center to meet the needs of your workload. So with that context, like, it'd be great to pull Mrunal up and see DRA
let's take
in
a look
action.
at this DRA. Welcome.
Thanks. All right. Okay, so I'm going to kick off the demo that we have recorded for DRA. So here we have an OpenShift cluster with GPUs and the NVIDIA DRA plugin installed in the cluster. So we basically need plugins to expose new types of devices, and here we are using the NVIDIA DRA plugin. So now we're going to run NVIDIA SMI to list the GPUs. Note that there are 4 GPUs, and each GPU has a different UUID. Now, in the past, as Derek mentioned, if you were to request a GPU, you would say nvidia.com/GPU, and then you'll ask for a number. With DRA, we gain the ability to specify the GPU based on its attributes. So in this example, it says, give me an NVIDIA GPU with the product name that matches A100. So you can change it to request an H100, L40, whatever you want. So GPUs are no longer devices that you just request by numbers, but you can go by its attributes. You can request a GPU by the amount of GPU memory your workload wants, or the number of GPU cores that your workload wants. So one more thing that will come in the future is the ability to get slices of GPUs as part of the DRA effort. So now we apply that resource template to the cluster, and then we have a pod here requesting that A100. So if you take a look at the last line, it just says resource claim template name A100. It's referencing what we created earlier. Now we start that pod, and we check the logs of the pod, and note that it got assigned one of the 4 GPUs that we listed earlier. Now we check the resource claims, and we see that this pod got a GPU allocated. We delete it, the resource claims get cleaned up. Now let's try with a real AI example. So here we have a VLLM pod with the IBM Granite model, and we're going to prompt it. And note that it's also requesting the A100 that we created earlier. So this pod is already running. It has a resource claim associated with it. And I'm prompting it with Salt Lake City is known for, comes back with its diverse and vibrant food scene with a wide range of cuisines to choose. So this is actually using the A100 in the cluster. So that's DRA.
Nice.
Thank you.
Yeah, I think now I get what you meant by it's following the pattern of CSI. You have this concept of plugins, this request concept.
Yep. It's very cool. And there's a lot of capabilities implicit in the model that are kind of interesting in the sense that in the past, pods can have many containers in them, and you can have init containers, application containers, sidecar containers. There's no shortage of richness to the pod model in Kubernetes. But you couldn't previously share a device among multiple containers in a pod, right? So one of the nice things actually with this DRA model is that just like a volume can be shared among containers in a pod, your devices can actually be shared as well.
Yeah.
And that's actually really important, like this concept of sharing. And this comes up a lot because these devices are expensive. So
Sure.
I don't know, Mike, how familiar you are with the Quota systems these days.
So that's interesting. I think the first time I ran into you was in 2017, 2018, where I needed somebody to explain mill cores to me and how this Quota system worked in Kubernetes. And you ripped off all the mystery and really made it make sense. But yeah, I know it's a passion for you in this area.
Yeah, well, I've known you longer than that, but maybe I didn't make an impact before that point. But Mrunal and I in particular have been involved in resource management in Kubernetes for a very long time. Like we both are technical leads in the node SIG upstream, and a lot of what the Kubernetes resource model is today are a lot of consequences of our input and others. So you're welcome, and I'm sorry at the same time. And one of the things that I know I worked on originally in the beginning of Kueue was when we wanted to build OpenShift around Kubernetes. That was a big leap back in OpenShift 3. We had to support some way of giving fair access to resources among tenants on the platform. So personally, one of the things I had gone and worked on is, we need namespaces in Kubernetes. You need a way to subdivide the cluster. And then the second thing right afterwards was, I need a way to quota how much resource a person can get access to. And the requirements at the time were not necessarily one-to-one as they are today. So resource quota in Kubernetes is traditionally around this idea of just capping excessive consumption. So you can say a user gets this much CPU, this much memory, this much disk across the set of pods they might run in their namespace. And for a lot of organizations that are just running traditional request web serving apps, resource quota in Kubernetes is great at like preventing abuse and runaway resource consumption. With something like GPUs, though, these devices are really expensive. And the priority is to optimize for throughput rather than for restricting overeating. So there's a project right now that we at Red Hat are tracking closely and working on the upstream called Kueue. And its whole idea is inverting the resource quota model. So
Kueue with a K.
Kueue with a K, right? So get in line, but that line needs to move as quickly as possible. And so Kueue inverts the quota model in the sense that it says, rather than limiting Mike and Mrunal and Derek to just getting 3 CPUs, its job is to make sure that all those CPUs are exercised as efficiently as possible. So it also has this concept of giving priority among parties. So Mike, he's not an engineer, so he doesn't get as much access to CPUs or GPUs, but if he needs it, he can have it. But if I come in and I say, no, I really need to do something, I want to stop Mike's ability to borrow from me so that I can claim back what I need to do to get my job done. So with something like a GPU where you have maybe multiple teams in your organization, someone's experimenting with some light inferencing, or someone's experimenting with a training job, you want to make sure that those teams have fair access to resources, but if those resources are underutilized, give as much of it as possible. So Kueue is a project that is really oriented to that concept of high throughput quota management. So why don't you, Mrunal, walk through a Kueue demo?
How does Kueue work?
All right, so here we have the OpenShift cluster with GPUs. Again, we're going to list the number of GPUs here. So there are 4 GPUs, and Kueue is installed on the cluster. Now, we're going to define 2 queues. So Kueue has a notion of a cluster queue, and you can define as many of them as you need. So we have 2 queues here. One is for the AI training cluster queue, which is the one where you are trying to train your model. So this is the more important queue. And we give it a quota of 3 GPUs. We can also assign it CPUs, 9 CPUs, and a memory of 36 gigabytes. And let's move on to the next queue. So this is the labs queue. This is where the engineers are experimenting, or they are running some bad jobs. So this is not as high a priority as the other queue. So look at the quota here. So this one is assigned only 1 GPU, but it also has a borrowing limit. So what it means is, if other queues in its cohort have spare GPUs, it can borrow from there. So here, there's a cohort team AI, and both of these queues belong to the same cohort. So that way they can borrow and share resources. So now we apply these queues on the cluster. And to be able to actually access these queues, we create namespace level local queues. So there's a level of indirection here. So we create one namespace for the lab and one for training. And then we create local queues. So now we check both the queues and we see that none of them have any workloads admitted yet. Now let's run a simple job. This is a simple vector add Quota application just to see that our GPU is getting exercised. So now we see that it ran to completion and we're going to get the logs from the workload. And it says it did a vector addition and it ran to completion successfully. So now we'll run some sample jobs, and these jobs will just print the GPU that got assigned to them, and then they're just gonna sleep to simulate waiting. So this is the first job. This job is in the AI Labs namespace. So we see that now it's admitted. We create another job. So now 2 jobs are running in the AI Labs, and both the jobs are requesting 1 GPU each. And we'll check that the GPUs got assigned to the jobs. And we try to create a third one. Note that the third one cannot be admitted because there are no GPUs left anymore. And we see an error here that the borrowing limit was reached and it can no longer be assigned any GPUs. Now we start creating jobs in the AI training queue. So we create a couple of jobs, we check, we get a status of all the jobs across both the queues, and we see 2 admitted to both the queues and one of them is not admitted yet. So we're gonna get the GPU IDs for the other 2 jobs. And now, when I delete the third job in AI Labs, one of the jobs in AI Labs, the one that was suspended will get admitted. And it gets one of the GPUs that was used by another job previously. All right, so that's a queue for you.
Yeah. So DRA helps me get to the resources. Kueue helps me leverage them in a much more intelligent way than, say, the job controller used to, or any of the other priority preemption schemes that we used to have.
Yep.
This takes it to the next level.
Yeah, exactly. So for a lot of us here on the engineering side, trying to push the community forward, a lot of the work ahead next year around DRA and Kueue is getting them integrated nicely together. So DRA right now is still not yet generally available in Kubernetes, so you're seeing very hot off the press stuff integrated in the product. But that's a major focus for the year ahead to make sure that the 2 communities work well together. And then in addition, as we talked about, like the journey in Kubernetes around things like pods and jobs and deployments, there's a lot of interesting work going on these days around particular workload APIs to capture the types of primitives you will need to run things like batch inferencing and batch training. So it's exciting times ahead.
Perfect. So before we run out of time, let's move on to the next topic. Security is really bringing in a lot of requirements onto the platform. I think 2023 and 2024, we had a really large explosion of regulatory assignments coming towards the platform in general. A lot of it was out of Europe. A lot of it was out of federal governments like FedRAMP and various things. There was just always an interest to have different concepts of isolation, like namespace isolation, cluster boundary isolation, network isolation. Where do you see that going, and what do you think happened there?
Yeah, so how many people in the room run clusters today? Like if you just had a hand raised, I'm hoping some audience participation. A fair number of hands up. And how many people offer namespaces or projects to their teams and their organization as like a way of segmenting a cluster? And I still see hands up, right? So that, I would say that usage pattern was the dominant pattern of our user base, and probably still is for partitioning out access to clusters. It makes a lot of sense. And over the years, we ran into use cases though where customers would say, hey, I need a dedicated cluster for this scenario. It needs to run on the edge. It needs to run a particular workload that doesn't work well with others. And you started to see some movement towards internal users offering like a cluster as a service paradigm. So how many people within their organization maybe think that they've run a cluster as a service paradigm? Hands up, or it's probably, there's fewer hands, right? So one of the great things about that model, though, is like, well, namespace as a service, you're on a shared network. You're on, your workloads are running on shared nodes, and you have some sense of shared admin responsibility. And then you go to the cluster as a service model, you have each cluster has its own dedicated network, its own dedicated set of nodes separate from the other. And that's a very hard line security isolation boundary. So what Mike was referring to earlier is we're starting to see a nuance in the networking space asking for like a third way, where you want to have a network isolated workload among others on a common cluster. So how many people today run network policies in their cluster, if we raise their hands?
Yeah, it's common these days.
So for folks just so we're on the same page, by default, the Kubernetes networking posture has been that every pod by default can talk to every other pod on that cluster. Every service by default can talk to every other service. It was a very open, permissive network. And as Kubernetes has become popular in a lot of other regulatory restrained environments, you know, the community has worked towards putting kind of seatbelts or restrictions or barriers in place. And things like network policies are a nice way of doing that. But often, we would hear that pods need to attach themselves to a dedicated network. And traditionally in the past, that has been with things like Multis and running a secondary network. How many people might use that in the audience today?
Yeah, a second NIC on a node.
Yeah. So one of the things we're really excited about in the OpenShift networking space is we're introducing this concept of a user-defined network. And so what this will let you do is you have a common cluster, and let's say you partition it into a set of projects or namespaces representing your various tenants. With this evolution of a user-defined network and OpenShift networking, you can say tenant A has a different primary pod network and service network than tenant B, even though they're on the same cluster. So by default, for example, if you imagine Mike is running his workload in namespace A, and I'm running my workload in namespace B, and while I trust Mike, we're in the same organization, maybe the workload can be on the same node, by no means do I want Mike to ever be able to communicate to my pods over the network, right? And I could do that with things like admin network policies, but it actually is a fair bit of work to track down. And in some cases, Mike's app might need subnets and IPs that overlap with my app, right? So the better outcome would be, what if I could just give Mike his own network and say, go have fun with it and leave my network to myself?
I get my own CIDR range.
You get your own CIDR range, exactly. So with user-defined networks, that's exactly what we're rolling out right now in OpenShift today, which is going to give a really nice new network isolation primitive to these industries that are asking us to push towards that environment. So Mrunal, why don't you show folks what a user-defined network looks like?
Sure. All right, so we have an OpenShift cluster here. So we create two namespaces, namespace A and B. Then we are creating a user-defined network in network A for namespace A, and we'll create network B for namespace B. So take a look at the YAML here. So we are defining a layer 3 network. The role is primary. This could also be secondary. And then it has its own CIDR assigned to it, 103, 103.0.0. So now we create it, we check that it's been created successfully. Now we do the same for network B. So here, note the difference that we are using a different CIDR, 203, 203. The rest is the same, it's still a layer 3, and the role is going to be primary. So we have two networks created for the two namespaces, and we check the second network is successfully created. So now we are going to create a couple of stateful set apps and services, one in each namespace. So this is what we have running. So we have app A0 and A1 running in namespace A, and B0 and B1 running in namespace B. So we are inspecting the networks of the pods, and we can see that for network A, A0 got 103.103.03, and A1 got 103.103.51, and the role is primary in both the cases. Now let's check that app A0 can connect to app A1 within the network. So we do a ping, that works, and now we'll try through the service IP. So this proves that there's connectivity between the apps in the same network. Now we'll do the same exercise for network B. Note the IPs here, 203.203.34 and 203.203.55 for B0 and B1. Now we check the connection using ping, and then we'll check through the service IP. So we're just checking that there are no network policies. This is something you get out of the box with user-defined networks. So there are no network policies at all defined in the cluster. This is an overview of where we are right now. Now let's try connecting from a pod in network A to a pod in network B. And that won't work. Let's verify that we can still connect to the Kueue API server from the networks. So that's UDN. So Surya and Doug, thanks for the demos. They have a session later today. They're going to dive into more details if you're interested to learn more.
Thanks for that. So, what's interesting about this, and people are probably thinking, well, yes, network isolation, it's important. But you mentioned it slightly before, this IP address problem that we're having. And as we get more and more workloads from a diverse area of the businesses coming to the platform, they all seem to have their different requirement on the IP address. They all seem to like, hey, I definitely need my own. And before you would have to plumb up that secondary network in Kubernetes, you would have to go through the trouble of assigning it. This allows you to really automate a lot of that and establish these CIDR control ranges within the namespace that really opens the door. And we're seeing one particular area. Can you talk about that,
Yeah,
that workload?
One of the amazing things to me is just how popular virtualization is as a workload these days on top of Kubernetes. It's almost a mind inception a little bit. But as virtualization workloads come onto Kubernetes, you have a lot of unique networking requirements, traditionally in the virtualization domain, where stuff like the user-defined networking feature comes to heart. So often virtual machines are traditionally isolated in their own discrete networks. And so if you're bringing those virtual machines onto OpenShift, your first question is, well, how do I recreate that? So why don't you, Mrunal, show virtual machines and persistent IPs in action?
All right, awesome. So we're going to demonstrate VM migration here, intersecting with UDN. So we have a Fedora VM running in the cluster. This is the user-defined network for it. Note that it's a layer 2 network. So the same layer 2 is going to span across nodes. This makes it easy for us to migrate VMs because the VM can have the same IP even if it moves across nodes. And then it has a persistent IP associated with it. And the IP is 10.0.0.8. So let's console into the VM and check its IP address to make sure it matches. So we see it's 10.0.0.8 indeed. So we're going to start pinging this IP address from another pod. And then we're going to watch the pods. So we have our Fedora VM on 10.0.0.8, and now a migration has been kicked off. Note the pending for the new VM. So the VM is being migrated from 10.0.32.44 to 10.0.11.203, while the ping is still working throughout the process. So eventually, the one you see down there saying succeeded, it ran to completion, and now it's migrated to another node, while our ping has been working throughout. So that's live migration with UDN.
Yeah, thanks for showing that to me. Well, I mean, in the sake of time, we should move on to the next topic, which is virtualization. And virtualization has been an interesting journey for us. I would say we start in the ecosystem, the KubeVirt project, and I think it was, what year was that? It was before 2020.
Yeah, I mean, I remember having discussions with folks in the community back in 2015 about this idea of what if you could run VMs on Kubernetes.
Yeah. And then we come out with an official product with support and services built around it in 2020. I would say from 2020 to probably 2023, people were very interested in modernization of virtualization. And a lot of people think I'm going to start immediately talking to them about containers. That's not what we're talking about. We're talking about using a virtual machine in cloud-native patterns, where you wouldn't necessarily need user-defined networking if you were doing that, or you wouldn't necessarily need some of these other features. But then in tail end of 2023 and in 2024, people said, look, I understand that is a future and I'll get there, but I want to migrate. I want to take my legacy virtualization platform and I want to bring all the patterns that it has, new application patterns, and bring it to the platform. And that's what we've been really working on, like getting just a straight migration of what people have today in virtual machines over to the platform. That was a big driver for the user-defined networking. What else do you see happening because of that?
Yeah, so the KubeVirt community within the broader CNCF is amazing, right? And it's got a rich ecosystem of folks contributing and consuming. And one of the things I really liked about the community, if you go look on its documentation homepage, is they discuss this design concept they call KubeVirt's Razor, which is like if something could be done in Kubernetes to support virtual machines that the whole community could benefit from, then they'll do the work there rather than the KubeVirt community. So in the earlier demos you saw, Mrunal was showing what were actually virtual machines, but they were just appearing as pods on the cluster. And that idea of a virtual machine as a pod is so powerful because it means all the other things in the Kubernetes ecosystem that empower everyday application pods, as we know and love them today, have a role to play in virtualization. So whether that's in the CNI layer where you're doing custom networks like this, at the L7 layer where you're routing network packets to your various applications running your VMs, KubeVirt can take advantage of all of that. As we look ahead in the year ahead, there's a lot of interesting things happening in the Kubernetes resource management space that we see KubeVirt being able to take advantage of. So things like being able to in-place resource resize your pods has been a long-running request for traditional application images running on the platform. What we'll show you today is KubeVirt can already handle those capabilities to dynamically hot plug resources. Or traditionally, VMs take advantage of things like swap to drive heavy overcommit. We've been working hard in the community to get swap to general availability support so that all our application images can take advantage of it. So why don't you, Mrunal, show folks OpenShift virtualization action.
Okay. So here we have an OpenShift cluster, and we are working through the console for this one.
No command line? Come on, Ronald.
So we're going to go and look at the templates that you can start your VMs with. So this is a RHEL 9 template. And we start a VM using RHEL 9. So it's going to get loaded quickly, and then we'll start seeing things on the console. So you can see text scrolling by in the console as the VM loads up. Now we switch over to the console view so we can see the VM. Note the node here because we're going to start a migration. We saw in the earlier demo that we migrated a VM from one node to the other. So the thing to note here is this is all using Kubernetes style API. So even migration is a Kubernetes style API that we can apply to kick off a migration. This is to show what's happening behind the back, but you can just click a button and the migration can be kicked off that way too. So the migration is getting scheduled. It's running. Note the node which changed. So now we're going to go and change the number of CPUs and the memory assigned to the VM. And that's showing hot plugging functionality. Behind the back, it's actually doing a migration. And as Derek mentioned earlier, right, as we mature the in-place VPA feature in Kubernetes, we won't have to do a migration. We'll be able to just resize the pod hosting the VM dynamically.
So in that sense, a VM is like a stateful workload. You don't want the VM to restart, you don't want anything to change, but you just want the new resources.
Yep, exactly. Like the reasons why you may want to migrate is you want a new storage class, or you want more resources today, or your cluster is getting upgraded, and because of that, your VM just gets moved without disruption.
Excellent. We sometimes joke that KubeVirt is the most kube native workload as it's supporting all these actions.
Yeah. You can really see how it needed the platform to change in all these little areas for it to really pull off a use case.
All right, so let's see that we can also actually run Windows here. You need to bring your own license, but it works seamlessly within KubeVirt. So we're going to give it 2 CPUs and some memory, and then start Windows. So Windows is booting. We can see that in the console. Wow, you actually see the Windows welcome screen. Isn't that awesome? Yeah, you can interact with it through the console directly. And this is all powered by just plain old Kubernetes pods, right? Your VMs are working just like any other pods within the cluster. So you're able to access the server manager and inspect the memory and the CPUs assigned to it. So similar to how we modified the Linux VM, we can also modify the Windows VM, and it'll all get hot plugged, migrated seamlessly. So we go back to the console and check whether it got updated.
Now the interesting thing here, Mrunal, is like just because this is a pod on the platform, all the native monitoring capabilities we have in OpenShift today to say how much CPU or memory or actual utilization this VM is consuming works the same way as a VM as it would for an application container, right?
Yeah, it's all using the same C groups and everything that you use for your regular pods. And now we can see that the memory got updated for this Windows VM. Then finally, we're going to talk about one more feature. So we have the descheduler, which works today with KubeVirt, just like it works for the regular pods. However, we are working on making this load aware. So there's something called as PSI that you get with cgroups v2, and the team is working on utilizing PSI metrics to do load aware descheduling.
So rather than triggering all these live migrations as a manual action when you want to do maintenance, if you just want to rebalance utilization across the cluster,
Yeah.
the same component in upstream Kubernetes to deschedule application containers is going to deschedule
Yeah.
VMs
as well. Yep.
transparently and using actual load-aware utilization. That's pretty awesome stuff.
It is. Yeah.
Yeah, so that was the demo.
Great. Well, thank you. We should wrap up on virtualization. Any final thoughts of the session? I think we're coming up on time.
Yeah, I mean, for me, the takeaways are just like the sense of potential that you have on Kubernetes and OpenShift today is immense. And the ecosystem that has grown around the core project to support a wide variety of use cases. And the three we touched on here around AI, networking, and virtualization are just a subset of what I thought all our users are using today on the platform.
Yeah.
Even things like Kueue that Mrunal was showing earlier, you know, it's very common you might be using pipelines to migrate VMs onto your cluster, and to have resource sharing among your VMs and your migration jobs is something that we could see Kueue actually fulfilling in the future. So it's really cool to see all these projects come together to provide like a good foundation for everyone to support their use case.
It is, and you know, I think we start the session talking about platforms evolving, and platforms are completely pointless without workloads, right? Why would you even have a platform if you didn't have a workload? But at the same time, the workload is going to bring requirements to the platform, and it's going to cause the platform to grow and to change over time. And that's where we need everybody's help in the room. That's where we need a strong open source community to bring the projects that we saw to bear, and the ones that we haven't even thought of yet to bear as more and more workloads come to the platform.